Hi everyone, good morning. So I'm very aware, as we've just been reminded, that I'm standing between you and lunch, so I'll try and do this as efficiently as I can and get you to the sandwiches. So as I said, Director of Analytics at Seams, so we're part of the Arcadis group. Arcadis likely to be one of the biggest consultancies you've never heard of. But in essence, we are a design and engineering consultancy with a footprint all over the world. So we do a lot of work in infrastructure, so with kind of airports, roads, city planning, railways, kind of water utilities, electricity companies, those sorts of things. So what I wanted to do is kind of tease out a kind of small handful of some of the projects that we've been working on recently. We kind of work on quite a few different things, but I've kind of picked out a couple of kind of ones that I found interesting anyway. Just to kind of take you through and kind of give you a bit of exposure to how we're doing these. You know, we're applying data science and analytics kind of in the real world of kind of more traditional sectors, if you like. So when we talk about kind of infrastructure, we're talking about the supply of water to our taps and our showers and those sorts of things. The supply of electricity to our plug sockets. The transport systems that we use every day, the telecommunications networks that we use every day. So in essence, the kind of the fabric of modern Western life, really. If those things break down, we get very used to them. If you look kind of globally, what's sort of spent in that space. So there's a bit of work done by McKinsey, looking at around the world how much is spent. About $2.5 trillion every year is spent in those spaces, on the water, power, etc. Which is a lot of money every single year. Now the problem is, if you actually have a look at how much money should you be spending on those things every year in order to kind of keep up with the deterioration of those assets. They're all, a lot of them are getting quite old. The kind of growth in populations in cities and other bits and pieces. You come up with a number that's more like $3.3 trillion per year that you should be investing into those basic infrastructure needs, if you like, to maintain Western civilization. And that is a big gap. That is a very, very big gap between those two numbers. And that's really kind of where we focus with a lot of these sort of companies is how do you close that without spending tons more money? How can you do things more, in a wiser way, make better decisions, clever decisions, so that you're actually achieving more with that $2.5 trillion than you are today? But this problem's heavily compounded. We've already got a problem to start with, but then when you kind of start to account for the impacts of kind of climate change, massive population growth globally, and those sorts of things, these challenges become really, really quite important to face and deal with. And in essence, I'm going to kind of tease out a couple of projects where we're kind of touching on these. So I'm going to start very much in the water utility space. So again, in the Western world, we're kind of used to this idea that you switch on a tap and water comes out. And we don't really think too much about that, and we don't really think too much about what happens behind the scenes to make that actually happen. But it is actually amazingly complex. And I don't know if any of you caught the lightning talk from my colleague Dave Smith next door early on, where he talked about kind of real-time management of supply and demand of water. It gets quite complicated, and it's surprising just how close you come sometimes to the water not coming out the tap when you switch it on. So there's a lot of work that goes on there. I'm going to talk a little bit more about strategic planning. If you didn't see Dave's talk, come over to our stand. We'll talk you through it. It's a really interesting piece. I'm going to talk about strategic planning for water. So a typical water utility has got a whole range of different assets. So you've got all the kind of the pipes buried in the ground. You've got the pumping stations. You've got water treatment works. You've got reservoirs. You've got extraction points, boreholes, all sorts of things going on. A lot of assets that they have to maintain, and all of those assets need to be working for the system to work. So we do a lot of work with water utilities, and have done for many years, to kind of help them to understand how to optimise their spending around those assets. So they're driven by various different metrics. How often do the pipes burst? Things like water discoloration events. How much does it cost to do their maintenance, and those sorts of things. And we build lots of models on behalf of the water industry. To help them predict actually how assets are going to degrade over time and what they should do in response to that. So we would look at, typically they have quite a lot of data on historical failures and those sorts of things. We take that data, we build predictive models from it. So based on the age of the pipe, the sort of soil it's buried in, maybe some of the things that are going on with that land use and other things. What's the probability of that pipe bursting or leaking or any other kind of metric in the future. And what are the options that you could take in response to that? So you could decide you're just going to dig a small hole, you're going to do a patch repair on it in response to a leakage. You could proactively go in and kind of improve a section of pipe, or you could choose to dig up a massive long section and replace an old cast iron pipe with a new plastic pipe or something like that. Lots of different options. And what we do is we build those models and then we offer them up to a genetic algorithm to kind of allow it to search that decision space to find the optimum decisions that you could make for that pipe. And that all works really well. And actually we find that with fairly simplistic predictive models, just so often sort of simple logistic regressions and other things from the data, that we can actually quite accurately predict sort of bursts and leakage and other things and optimize that. But then what happens if you want to take that a little bit further? So if we look at one of the key headlines within the water industry is about managing that headroom, that demand-supply balance. So here in the top left, we kind of see before we apply any solutions, what is expected to happen with water availability. So we can see there's some sort of big event that happens in 2030 that means that we go from having net positive amount of water in the system to negative water, which doesn't really make much sense, but you can understand the connotations. So clearly there's something going on there, maybe the opening of some big housing development or something like that's going to suddenly push up the demand or whatever it is. And on the right hand side you can see the kind of response that the system's had to that in terms of interventions, which is now kind of dealing with that shortfall and closing that gap. Now the problem is that what we've done here is created a whole bunch of different projects that are going to need to be implemented in order to manage that problem. But each of those projects comes with a level of uncertainty. So if we look at, we've got scheme 1, scheme 2, scheme 3 there. Each of those will have a cost, an assumed cost of how much it's going to be to deliver that work with some uncertainty, plus minus 25%, 5%, whatever. It's going to be a certain build time. So particularly for big assets, if you want to build a new reservoir, that does not happen overnight. That could be 5 years construction to create a new reservoir. So there's a delay between starting work and actually seeing the benefit of that work in terms of the supply and demand. And similarly, there's uncertainty around actually what are you going to get in terms of megalitres per day of supply or whatever it is from that benefit. So it's a big uncertainty analysis. And what we need to be able to do is pull together an overall program of works that accounts for that uncertainty, to make sure that actually we're still selecting the right things to take forward to achieve the overall demand. So what we do is we might have hundreds of different projects within this list that the water company might want to deal with. So what we do is we sample that uncertainty and we use a Latin hypercube to do that, just to keep the numbers controllable. And we run that, so we effectively create lots of individual models, each with a kind of Latin hypercube-driven perturbation of those starting points. Offer that up to a genetic algorithm, come up with a unique program of works in response to that change. Now, if we look at a particular project in this case, so we've done 100 iterations of the starting points, and we can see that left scatter plot there. So the green points are kind of items when the project has been selected in the overall program, and the reds are when it hasn't been selected in the overall program. And in general, this kind of makes some sense to us because we say, okay, well, actually, so we've got the cost of the work on the y-axis and the benefit that you're getting on the x-axis. And clearly, if the cost is high and the benefits are low, it's not often being selected. It makes intuitive sense. But also, you can see that actually there's some reds kind of on the right-hand side where actually the benefit's quite high, the cost's not terribly high. And that kind of happens because actually this is quite a non-linear problem. So it does depend on what else is going on within the overall program. So in those cases, you've probably got some other project that's come up that the sensitivities meant that actually it's going to be really cheap to deliver and really high benefit, and therefore this one gets squeezed out of the overall program given the constraints. So this is all great, and we can kind of look at that across all the different projects that we've got kind of on our list, and we can look at in terms of the uncertainty, how often those projects get selected. So those ones at the top are getting selected in 100% of scenarios. So it doesn't matter how much we perturb the starting point; those projects always get selected. They're pretty much no-brainers. But actually, what you can see is, moving along, is actually they're often getting selected in different years. So this is a long-term horizon we're looking at, and sometimes I might get selected in 2015. Sometimes it might be 10 years, 11 years later than that. So actually, the uncertainty is starting to really drive a decision about when you should do that. You then got projects further down that list that are actually only getting selected in kind of, it's a 50-50 chance as to whether or not they go ahead or not. So actually, there's a lot more information needed. You might need to narrow down the uncertainty about what you're going to get for those projects before you select them. So far so good, but actually, we decided that's not difficult enough. So actually, what we also need to account for, because this is a long-term strategic piece of work, is we need to account for things such as climate change, population change, and those sorts of things. Now, this opens up a whole other level of kind of complication, because actually, we don't really necessarily know precisely what the future is going to look like from a climate change perspective. We don't necessarily know what the population growth is going to look like. So at one extreme, we could account for extreme levels of climate change, mass migration from other countries into the UK in response to that climate change. And that drives massive rise in demand for water and a significant drop in the supply of water because we're getting less precipitation, whatever that happens to be. So at one extreme, we could have that. I'll come to you in a second. At the opposite end of the spectrum, we could maybe climate change doesn't end up being much of a big thing at all, doesn't particularly change the level of precipitation, but maybe there's, due to no deal Brexit or something like that, everybody leaves the UK. The UK is taken over by stray cats, and because they lack the opposable thumbs to work the taps, the demand for water just drops off a cliff. In which case, we really don't need to worry so much about this. And there are clearly more realistic scenarios between those two. But so what we need to understand is all of the different potential outcomes in terms of that supply-demand balance. So, did you want to ask a question?
Can you just explain how to read this chart?
Sure. Yeah. Okay. So what you've got here. So a list of projects down this side. Total, so this is how many, in all of the different scenarios that we've run. So in this case, we've run 100 different scenarios based on the Latin hypercube for this particular climate change population scenario. This is how many times it's been selected. So these ones at the top have been selected in every single iteration. So out of 100, it's been selected 100 times. Here we can see, so these are by year, 2020 onwards. So here we can see what percentage of the time is it selected in that year, because it's the genetic algorithm is making a very specific statement about it's this project in this year. So what you can see here is this one at the top may be pretty much a sure bet. You definitely want to do this project, but actually when you want to do this project is very much an open question, because actually you've got a massive spread in the timings of that. So clearly in some perturbations, leave it right until late in the plan, and some it's really important to do it quite early on. So that's effectively what that's saying. Right. So we're coming back to the climate change and everything else. So if we look at what the potential future deficit of water might look like, clearly we've got a whole bunch of different scenarios within that mix. So what we then do is we break that down, look at the kind of 20th, 40th, 60th, 80th, and 100th percentile in terms of how bad that could be. And what we're looking at here is, from any starting point, what could the future look like? So how might we adapt that? So actually, we might just choose to follow. We'll start off with a kind of fairly optimistic scenario, but at some point in time, we might decide we have to pivot our strategy onto something that is better suited to a more extreme scenario. So the point here is we're not stuck with one strategy for the next 30 years or whatever. What we want to understand is at which point could I pivot from one strategy onto another without losing too much ground. I haven't spent too much money on projects that I don't need anymore, and I haven't not delivered projects that are really quite critical to me. So the point here is that we can navigate through this grid in a whole manner of different ways, depending on how actually the evidence starts to become available to us as time goes on. So we're pivoting from one strategy to another. And actually, when you break it down, there's lots and lots of different ways that you can move through this potential scenario. And what we want to do is test all of those to understand, actually, from an optimization point of view, where should we start, and at which points could we change our strategy. And that's exactly what we do. So we run through that. We effectively break that up into thousands and thousands of individual models, each connected to a genetic algorithm. We fire that off to a farm of servers and let them crunch away the problem, and then we bring all that data back, and then we explore that and go, okay, well, actually, what does that tell me? So So in this case, we can see this particular scheme 65 here. It gets selected, doesn't matter which of those scenarios we look at, always happens, and it's always happening in the first year. So clearly, from a planning perspective, just get on, just deliver that one. There's no uncertainty around it at all. When we get down to scheme 30 down there, we can see actually it's always getting selected, but the timing is really quite critical. So clearly, if we're looking at the more extreme climate change projections, we need to do it really quite early on. If climate change isn't quite so bad, we can do it a bit later. So we can start to explore those questions and again start to set that overall strategy about at which point, what's your safe program that you can start with now, and where are your key decision points at which you've either got to choose to stick with your current strategy or pivot to a new one. So that's water. I'm then going to talk a little bit about rail. Yeah.
What geographical area is that?
So that was one water utility. So
So that would be like Thames Water or Anglian Water
yeah,
or something?
yeah, it was, yeah.
Part of England?
Yes, yeah. Okay, so I'm going to talk a little bit about railways now. So, and this picture, when I put it on the slide deck last night, it made me chuckle slightly. So I worked in rail for a good chunk of my career, and one of the things I noticed that when you ever see a photo of people working on railways, more than half the people will only be watching somebody else doing some work. Now this bucks that statistical trend because this guy with the tape measure is clearly under serious scrutiny, so hopefully he doesn't get that wrong. But mark my words, every time you see one, you'll watch out for it now. I guarantee you more than half. Anyway, so we do a lot of work for rail companies, kind of all over the world. So the first one I was going to press the right way. The first one we're talking about, so as a part of Arcadis, we are part of a company called Asset Rail, which actually maintains a good chunk of the railways in the Netherlands. And a piece of work that we did there was looking at a particular issue they had around failure of switching machines. So effectively how you move from one piece of track to another. And so they had a lot of failures, but it was very difficult. It wasn't kind of consistent. Some you had hotspots of failures in certain areas, and trying to understand that a little bit. So what they did, railways are generally pretty good. They have quite a lot of data to work on. So what the team did is they pulled in that data, the historic failure types, the asset types, the usage of those assets, things like the local geography, precipitation events, all these sorts of things. And what they did is they trained a random forest on that to try and kind of come up with a predictor for what's going to be the rate of failure of those assets. And as you can see here, when overlaid, so they trained it on 80% of the data, tested it on 20%. And what you can see is a reasonably good fit for the actual events that were happening. And what they were able to do is show that the worst 20% of switches kind of accounted for 60% of all disruptions, and the best 50% were less than 20%. So what they did with this was then kind of redesigned the maintenance regime for those switches. So those ones on the left-hand side get much more maintenance, and the ones on the right had reduced maintenance. And as a result of that, they were able to kind of effectively do as much work, but deliver a far more reliable service by actually focusing on the ones that were actually causing the problem. In this case, actually, it turned out that one of the biggest predictors for switch failure was actually whether it was geographically in a bit of a dip. So what was happening was it would rain, all the water would run into the dip and effectively just short out the system and cause all sorts of other problems. So that was a fairly simple problem within the rail space. We've also done much more complex ones. So this is where we're looking at an entire rail network. So we're kind of going to cross the pond. We're going to go over to the US now for some work that my team did there. And we were asked to effectively model the entire railway network. So everything from the passenger trains to the computer terminals, to the ticket vending machines, to the vans that the staff were using to get to work. And they wanted the whole thing in one model so that they could optimize investment across the network. So they could decide, well, actually, how much do I want to spend improving my track versus my stations versus my level access, all those sorts of things. Now this became, that was quite a big, complex model. Again, had to kind of learn lots of different rule sets about how fast different assets degraded. We had to kind of do a lot of work with the client to actually understand the relative criticality of assets. So how do you compare the criticality of a train to the radio that the driver's using to the computer terminal that's in the station? Kind of so we could get the right balancing across the entire network. In this particular example, it was made even more complicated by the fact that this particular railway had the most convoluted funding structure you've ever seen in your life. So it was all very well to predict at some point in the future you were going to have to replace this asset because it was going to fail. But the point at which you decided that you needed to replace that asset, you had 22 different funding streams that you could select from in order to pay for that replacement. Now, those funding streams all came with really kind of strict rules about what sorts of things you were allowed to spend them on and what things you weren't allowed to spend them on. So some of those would say you're only allowed to spend it on, track assets, or you're only allowed to spend it on assets that improve level access in stations, or something like that. Other funding sources were only allowed to be spent within certain geographic regions. So you're only allowed to spend it in District A, District B. Others, some of them were secured funding, some of them were competitive funding, so those pots of funding would only become available if they hit certain performance benchmarks, and all these. So effectively, we had to create a model that could deal with all of that complexity, and then offer it up to a linear optimization algorithm, and then solve that for the next 15 years to say, actually, where should you spend your money over the next 15 years? And that's what we've got here, which I find quite hypnotic to watch. But in essence, what the model's doing here as it steps through is it's kind of going through all of those different funding sources, and it's remapping those based on what the linear optimization algorithm has selected to be the best way of achieving the overall reduction in risk that it's looking for. So some quite complex stuff there, but again, just about making slightly smarter decisions about, okay, how do you want to spend your money? Okay, next one. So, not very a sexy subject, but waste collection. We're still on the opposite side of the pond. So this is our team in New York. Now, one of the problems they have there, they've got a free market kind of setup for commercial waste collection. So you've got over 100 different companies providing services, taking away rubbish from commercial properties. So these are kind of restaurants, shops, offices, those sorts of things. So this is a very typical example. So this is one strip mall in the US, and you can see each of those bins has a different company's brand on it. So you can almost imagine the queue of lorries outside to come and pick these things up each week. And so what they wanted to do is they kind of think, okay, well, this setup is fine. I'm sure each of the 100 companies is probably optimizing their route to some extent to try and pick up as many customers as they can in the shortest distance and make sure the lorries are full and all these sorts of good things. But actually, is that the optimum for the city? Actually, how far are they having to go? And when you worked it through, you realise that actually each of those lorries was probably travelling over a mile per customer that it was actually serving. So they were covering quite broad geographic areas. And in fact, if we map out, for each of those companies, this is kind of a map of where they were going, on a given night. So each of the different colours is a different company, etc. And you can kind of see they're just all over the place. There are some kind of broad kind of regions where the yellow's at the top and the blue on the right hand side, but they're actually just all covering everywhere. They're just covering an enormous amount of miles. And again, that's just because they're all competing with each other to get that next customer and that sort of thing. And they're almost not too worried about where that customer is and whether it kind of works for them. And when you start to look at, okay, where are the customers, you kind of get the feeling for what the problem is. So there's a massive kind of concentration on Manhattan Island of commercial properties there that need their refuse collecting. As you get outwards, it gets a little bit more sparse. So the bit that we wanted to explore here was actually if you change that model, so rather than making it a free-for-all for 100 companies to get to 130,000 customers, what if you broke it up into zones and say actually you can bid to work in a particular zone? So this is effectively what was explored. So say, okay, well, fine. So we'll break the city up into these regions, and each of those companies can bid to be a supplier in that region. Now, the problem they had there was actually how granular should you break the city up in order to do this efficiently? So, if you have big chunks, it's going to be less efficient. So you're still going to get that problem with trucks covering a lot of miles, but it's going to be less disruptive. So actually, bear in mind, there's a lot of people involved here. So there's 100 companies. You could easily send some of those bankrupt by making some of these changes. There's a whole lot of customers that are going to have to switch their provider as a result of this decision. So actually, you want to minimise that disruption to some extent. Whereas on the right-hand side, okay, we can go really granular, and we'll get really, really efficient. So we can get those routes to be really, really tight and efficient, and very short distances between customers. But again, highly disruptive. Everybody's going to be changing, and there's a big risk associated with that, and people may not like it. so they kind of searched lots of different kind of options there to find that, and they kind of settled on this idea of 20 zones, having explored quite a few different ones. So if we have a look at the result of that, so this is one particular kind of zone, Queens 2. So what you can see here is the hauler's routes to serve every customer that's in that red zone. This is in the original setup. This is how far all the haulers would have been travelling just to serve those customers. And then following the optimization, this is the route to serve the same customers from that perspective. From a traffic levels perspective, because clearly a key part of this was actually to reduce pollution in the city. So before and after, so this kind of shows how those routes kind of overlaid. So effectively, by doing this, you knocked 63% of the traffic out of the problem, in essence. And this was solved using various different methodologies. One of those was using the Here Maps API to kind of do the optimization of the routes and everything else, because it was quite heavily used by the suppliers at the time. Last one then, electric vehicle charging. So we're back over this side of the pond. We're working with Metropolitan Police. So Metropolitan Police are in the process of looking at how to transition their fleet of vehicles to electric to meet various commitments on pollution. I would just point out, I'm not saying that the Met Police are going to use Teslas. I don't. So that would be front page news, I reckon. But no, they're exploring this question of how to move to electric vehicles. So we had to gather lots of data to solve this. So first of all, we needed to understand, well, where are these vehicles? Where are they parked? So the Metropolitan Police has lots and lots of parking space, in essence, in their properties. So we needed to understand, well, actually, how many vehicles use those parking spaces? What sorts of vehicles are they, and how much are they used? So are they the sorts of vehicle that somebody uses it to in the morning and the evening, and it's sitting in the car park for the rest of the day? In which case, maybe you could connect it to a trickle charging system. Is it something that's out and about all the time? In which case, you might need a kind of ultra rapid charging system to get to be able to top it up in under 30 minutes. What's the power supply to each of these sites? Because clearly, if we over-specify how many charging points they're going to be in the car park, then we can very quickly overtake the amount of power there is available there, in which case we're going to have to upgrade the power supply, which brings additional costs and disruption and these sorts of things. So lots of data had to be gathered. Again, we took all of that information. We took the overall strategy that the police force had in terms of how fast they wanted to transition the fleet, and also how much money they had to spend. Offered that up through a GA to kind of come up with the best way of meeting that target within the money that they had available. We also had to explore lots of different scenarios. So effectively, one of the things that they were interested in is, well, actually, what should the mix of that fleet be? Do you want 100% battery electric vehicles, which is going to give you the maximum fuel saving, lowest emissions, or do you want hybrid vehicles, conventional hybrid vehicles in there as well? Because they could kind of tick the box either way. So we had to explore all those different possible fleet mixes and look at what the overall benefit was. So what this looks is the total costs of ownership of those fleets, and effectively what it's saying is actually if you're going to do this, it's kind of saying go big, really. So you can either go for 67% of your fleet as being battery electric vehicles, with the rest being plug-in electric hybrids, or go 100%. Effectively, don't go anything under 2/3 of the network as being battery electric vehicles, because actually it's going to cost you a ton of money to put all the infrastructure in, and you're not going to make the money back in fuel savings and other bits and pieces that you're looking for. So I've kind of gone through it very fast, and I'm mindful of time. So I really just wanted to give you a really, really quick flavour of some of the stuff that we're doing. There's all sorts of these activities going on around the world all the time. But it kind of just gives you a bit of a feel for actually how you can take data science and analytics and apply it into kind of questions that sometimes you wouldn't necessarily think of as being a traditional data science kind of question, and actually make a real difference to those areas. I'm out of time, so in essence, we can maybe take one or two questions. But if you've got questions, we've got a stand over in the corner. Come over and have a chat with us. We'll take you through stuff and give you more information. So thank you very much.
Any questions? Yeah.
Thanks for your presentation and really interesting examples. My question is about the water example. And when you showed the large grid and the different scenarios, I just wanted to understand, when you talked about the 100 scenarios, were they all equally likely? And I'm just trying to get a sense of, can you weight them? How? Just talk me through how you're picking your scenarios, please.
So the 100 scenarios were based on the Latin hypercube. So effectively, you needed 100 scenarios to sample the uncertainty. It's not saying that each of those is equally likely to be true. So clearly, there's some sort of bell curve of likelihood in there. Now, we deliberately didn't factor by that bell curve, because you then start, and particularly when you get into climate change and other debates, it becomes a little bit subjective. What's your favourite climate change projection, if you have one. So it kind of deliberately doesn't there, which is why we went down the adaptive pathways approach that I showed further down, which is actually saying, look, let's assume that each of those possible outcomes is equally probable. You might start off down a certain road based on your belief about likely scenarios, but actually your critical thing that you want to optimize is your future options. You don't want to be too far from any potential future, and therefore you want to be able to pivot from one strategy to another at key points without losing too much ground, which kind of neatly and politically sidesteps the problem of which version of climate change are we signing up to here.
Cool. Yeah.
Hi. Thanks for the presentation. Really, really interesting applications of data science here. My question is, okay, you build all of these models, but how are you sure that, for example, the waste collection solution actually takes place, and whether people are not just doing that to kind of tick a box? I mean, I'm a huge fan of data.
Yeah, you're absolutely right. You're absolutely right.
Just a small follow-up. Things change, obviously. For example, 1 year we have one perception of what's going on with climate change, and in 5 years' time it could be completely different. So, do you kind of go back and rerun those models, or how do you,
Okay, so so
transfer that into the future?
Yeah, okay. So two quite long-winded questions for just before lunch, but so picking up the first point, so actually getting people to implement the outputs is really, really challenging. So in essence, what we're kind of often find ourselves in the position of doing is we're doing all this fancy kind of optimization and that sort of thing, coming up with mathematically the best answer to the question you've just posed, and you're then passing it back to a bunch of engineers who have been doing this, since they came out of school and that sort of thing, and you're saying, guess what, guys, you're wrong. You've been doing it wrong all this time, and actually you could do a completely different mix of work, different time. That's really quite challenging, because actually if they haven't bought into everything you've done up until that point, they're going to go, yeah, what do you know? I've been doing this for 20 years. You're just a bunch of wet behind the ears data scientists. You have no idea what you're talking about. So we have to do a lot of work throughout with clients to make sure they actually understand what we're doing, why we're doing it, and actually understand the point that sometimes if you don't agree with the answer, it's because you haven't articulated the question well enough. So what normally happens is you come up with an optimized answer and says, okay, you should do this project, and they go, yeah, we shouldn't do that project because you should do this one. And when you start to tease into why you're saying that, oh yeah, because this gives you some additional benefit. Well, okay, fine, tell us what that additional benefit is. If we feed that back into the model, then guess what? The optimizer is going to say, yes, that is a good project to do, but it's also going to find you another 3 projects that also tick that box. So actually having that feedback loop is really quite important. So yeah, it's very, very much a case of kind of working through that with them, which kind of brings me to your second question, which is revisiting these things. So where, particularly that water example and that sort of thing, these are clients that we've been with for 15 years. So actually we've kind of started with them really, really simple. Can I build a model that predicts pipe bursts? Let's do that, and we can do it as a nice simple model that's very easy for people to look at the math behind that and understand what we're talking about and why that would be true. And then as they get comfortable with that, well, what can we layer on top of that to make it a little bit more nuanced? And what can we layer on top of that, Yeah, if we'd gone straight in with an adaptive pathways response to climate adaptation, they'd have gone, I have no idea what you're talking about, please go away and stop bothering me. So you've kind of got to take them on this journey. And it is very much that kind of, actually the constant what if. Every time you answer a question, yeah, but what if you did this, or what if this was an issue? So yeah, it's very much about those long-term relationships and making sure that actually what the analytics is doing is actually talking to the problems that they've got today.
Any more questions? Yeah.
What would be the largest areas going forward in the next 10, 15 years? What areas would be very critical to your approach?
Do you mean sort of what markets that we're interested in? Okay, so I mean a bit of background. So I work for Seams. So we originally started in the UK water industry, and now we've grown and do a lot of work in the electricity sector in terms of transmission, distribution, generation. We do a lot of work in railways and roads. But just over a year ago, we were acquired by Arcadis. Now Arcadis obviously works in all those sectors as well, but also has a much more of a footprint in kind of environmental areas and city planning, kind of airports. Those are kind of areas that we're kind of starting to kind of grow into, if that makes sense. Because actually, when you really break it down, the questions that that are being asked or the problems that they've got are actually just minor variants on the problems that we've had to deal with in water, in electricity, and railways. You just change the words, but the maths is the same. So for us, that's kind of that's the sort of where we see a lot of growth and that sort of thing going forwards. Is that we're in the beneficial situation that we get pretty much daily kind of bombarded with new types of problems to solve that we can then kind of go away and so the electric vehicle charging was one that kind of came out of the blue. Okay, we've never thought about electric vehicle charging before, but there's no reason why you can't hook up that to a GA and find a solution to that. That's fine. So yeah, we're kind of seeing growth in quite a lot of areas, and again, it's about that maturity as these as companies kind of get to a certain level of maturity and these questions become kind of front of mind, then they start to seek out people to help answer those questions.
Do you see willingness in multiple industries? Like, where would be the industry where they're really pushing for these kind of solutions?
It actually depends by country. So in the UK, historically the water industry has been pushing for this a little bit more because the UK water regulator was pushing them to get better. And so you've got to look for who's under the most pain. In essence, is really what comes down to. We're seeing a lot of interest from railways now for exactly the same reason. They're getting really, really squeezed. Exactly, and even outside of the UK, they're getting really, really squeezed. You go over to the US, and it's a very different set of sectors that are under that pressure and that sort of thing. So it's very much it's very difficult to go into a sector where everybody's kind of comfortable and kind of talk about this stuff because they just go, I don't get it and I don't want it. If you go somewhere where they're struggling, then all of a sudden this stuff makes sense and they kind of have to engage with it.
I'm going to take MC prerogative and ask a question. The previous slide that you had, the payback, do you know why it pays back at 67%, not at 83, and then again at 100?
Power costs. So as you transition from 67 to 83, you need to install a lot more power capacity into those parking points. So at that point, you need to jump straight over it because you need the additional fuel savings to justify it.
Neil, yep.
Thank you very much for your talk. I have a question about the team. So how does the typical team look like who is estimating this type of project? So is it a data scientist, a manager, somebody else on the team? How big are they?
So our team at Seams isn't enormous. So there's about 13 of us now. So typically, Seams itself is divided into two parts. So you've got the analytics team that I run, that do all the kind of the data science bits and kind of create the models and those sorts of things. And then you have the software team who create the software platform that we do all of this analytics on and allow us to sell it to customers. So typically we'll have 1, 2 sort of data scientists working on these projects. We'll have a kind of a lead and maybe 1 or 2 supports. But across the team we work fairly flexibly. So typically you'll have a lead for the project, but they'll be drawing on resources from across the team for a few hours here, a few hours there, because this person's got specialism in creating a dashboard that can communicate this result in the way that people are actually going to be able to engage with. Maybe this person's got specialism in automating an end-to-end analytics process through the system, all those sorts of things. So it's kind of a flexible approach which allows us to do quite a lot with a relatively small team. But we are growing quite rapidly.
I think that's all we've got time for. So big thanks to Dan.